right. Next, I'd like to take a look at what happens if we are trying to add several vectors together. Let's say that we would have, for example, an A vector, a B vector, and a C vector that look graphically like this. Then, in order to add them together, we could write, for example, D as our resultant vector is A plus B plus C. Notice here that we are putting little arrows over these symbols to denote that they're vector quantities that we are adding. And so we just do the head to tail addition vector sum successively for each one. Doesn't matter which order we add them in, but we move the tail of B, the B vector, such that its tail is on the head of the A vector, like that. And so then this would be A plus B would be C, would go from the tail of the first to the head of the second. But now we're adding a third vector, C, so we'll move that parallel to itself, like that. And then our D vector will go from the tail of the first to the head of the last vector, like that. And so then this would be the vector sum of A plus B plus C. Now oftentimes we are interested in getting our D vector in terms of components of A, B, and C. And so we could say that the X component of D would be equal to the X component of A plus the X component of B plus the X component of C. Okay, now the X component of A, if we define this to be an XY coordinate system like this, would be 0. The X component of B would be this part of B, Bx, and this part here would be By. And so the components then would be the parts of the vector that point in our xy direction, and such that when we add these together, bx plus by would give us our original vector b. And so we could get that then if we knew that this was theta b. We could say that bx is equal to b cosine theta b, like that. And then we could call this angle here theta c. We could similarly say that cx is equal to c cosine theta c, like that. And so our x component then of D in this problem would be 0 plus b cosine theta b plus c cosine theta c. And then you could do the same thing for dy. dy would be the y component of D. So this would be dx. That would be equal to ax, which is 0, plus bx plus cx. This would be cy. That. You can see here bx plus cx is dx, the way I've got it here, because ax is 0. And then for dy, we could say dy is equal to ay plus by plus cy. Okay, so dy then would just be the ay component, it's just a. The by component is going to be b sine theta b. And the cy component will be c sine theta c. Now here, we'll notice that the cy component is negative. And so we'll put that in as a negative. If we're measuring theta c from the horizontal down, that's a negative angle. Or you could say that this is the sine of negative theta, and then that would also give you a value for this quantity, which would be negative. So then that would give you the vector components of D. And so from that, you could then proceed to find D magnitude is equal to the square root of dx squared plus dy squared. And theta here, call this theta d, would be the inverse tan of dy over dx, because the tangent of theta d is going to be dy over dx. And so this is the way then that with a more complicated type of vector addition problem in which you had three different vectors, you could individually add up the x components to get the x component of your resultant vector. Similarly, individually adding up the y components of your vector to get the y component of the resultant vector, and then taking the magnitude of the hypotenuse. That is going to be the sum of the squareds of dx squared plus dy squared. Okay. Now, in the next example, what I wanted to do is talk a little more about units. Now, units of measurement are extremely important in physics. They are normally set up so that we have the distance measured in meters and the time measured in seconds. So we often refer to this kind of a set of units as MKS units. Now these are metric units in which the M stands for meter, the K stands for kilogram, and the S stands for second. So, although we will look at problems that are not in MKS units, the general procedure in most problems will be to convert eventually to MKS. So let me just first give you some techniques for converting units. Let's say that we have 1 year, and that's equal to how many seconds? Okay, so how could we do that? Well, one way of doing this is to multiply by equivalent forms of 1. Okay, and so we could first convert years to days by knowing that there's 365 days in a year. Now, this isn't exact, of course. It's 365.25, and then there's some more significant figures after that. But here, we're just interested in a reasonably accurate result. And then we could convert days to hours by noting that there's 24 hours in 1 day. Okay, so we're not changing anything here because this quantity and that quantity are equal, so what we're really doing is just multiplying by 1. But we're multiplying by a special form of 1 that changes the units. And so this, then 25 times 365 would be the number of hours in a year. But that's not what we're looking for. We're looking for seconds. So we can say then that there's 3,600 seconds for every 1 hour. Or you could do this in 2 steps. You could say that there's 60 minutes per hour, then 60 seconds per minute. But 60 times 60 is 3,600. And so that would save us a step by just doing this kind of a conversion. Then we can cancel out the units just as if they were numbers. And by setting up the equivalent form of 1 in such a way that all the units cancel out here except for seconds, we end up with an answer that's equal to 365 times 24 times 3,600, or 3.1 times 10 to the 7 seconds. Okay, so that's 31 million seconds in a year. Okay, now what if we had mixed units? For example, let's say that you had a speed that was equal to 60 miles per hour, and we wanted to know how many feet per second that was. Okay. Oftentimes, feet per second might be the unit of speed for, say, a BB gun, an airsoft weapon. And I used to play airsoft with my son, and he'd go, I just got a new airsoft gun, Dad, and it is 500 FPS. I go, oh, great. How many miles per hour is it? And so I had to figure that out before I realized that I didn't want to play with it. So how would we do that here? Well, let's convert miles per hour to feet per second, and then that'll give us a conversion factor that will help us figure out that problem. So here, first let's convert miles to feet. So we can say there's 50 to 80 feet for every 1 mile, and there's 1 hour for every 3,600 seconds. So that gives us 60 times 5280 over 3,600. So the 5280 over 3,600 is the conversion factor that gets us from miles per hour to feet per second. So that gives us roughly 88 feet per second, or 88 FPS. Okay, and so that means that there's essentially about a 1.5 conversion factor between miles per hour and feet per second. So the feet per second is the larger number, and so about 2/3 of 500 then would be maybe 360 or 70 miles per hour, which is enough to go right through your any kind of single layered clothing, and if it hit you in the face, you'd have a welt for a week. So I declined his offer when he got such a powerful BB gun. All right, so that's how we deal with these kind of units. Sometimes it's a little more confusing if you're going to, say, square or cubic units. Like, for example, we might want to know if you had 10 square centimeters, how many square meters is that? Okay, so how would you do that? Okay, well, 10 square centimeters is going to be just a small fraction of that in square meters. And so the way to convert is to write an equivalent form of 1, in which here you have the conversion factor, 1 squared meter squared for every 100 squared square centimeters. So here, in converting to square units, we also have to square the conversion factor, because 100 square centimeters is 100 by 100. Okay, so that's 10,000 square centimeters in a square meter. Because you'd have to go 100 this way, but you have 100 rows of 100. So that's 100 times 100. Okay, and so what this gives us then is 10 times 10 to the minus 4, or just 10 to the minus 3 square meters. So 10 square centimeters is just 1/1000th of a square meter. And if you were going to do this with cubic units, you would then cube the conversion factor. And so those kinds of conversions can be a little tricky if you don't have that rule in mind. So those are the main subjects that I wanted to cover in lecture from Chapter 1. Now, one thing that you will notice from Chapter 1 is that there are sections on the dot product and the cross product for vectors. And although we will get to those later, and I'll come back to those, I don't think that that's necessary right now for us to proceed to Chapter 2, which is motion in one dimension. Okay, so what does this mean, motion in one dimension? Well, it simply means motion along a line. So this is the simplest kind of motion that we can deal with, is motion in which we're going, say, either across and back in this horizontal direction, or typically up and down. Now, one dimension could also be along a line like this, too. But usually we can define our coordinate system in such a way as to have the horizontal direction be the direction of motion, or the vertical direction. And that tends to be the most natural way to handle these kind of problems. Okay. And so this is motion along the line. Okay. And so what I'd like to do to illustrate this is set up a problem in which we have motion in the x direction. And I'm going to set up a coordinate system here, which is a scaled version of a real situation, in which I'm going to define 0 here to be the origin of my coordinate system. And then I'm going to call this 1 meter here, and this 2 meters. So this isn't quite right in terms of the scaling to a real life problem. But it's not going to be like that on your note paper either. It's going to be just a scaled version of the real situation, just like on a map. You say 1 inch equals 5 miles or something. And then here on this side, I'll put -1, -2, -3, -4. Okay. And so we'll confine the motion then to be motion along this horizontal line, in which if I stand here, we're defining that to be the center of my coordinate system, or the place where we start. Okay. And so let's see how we could graph different kinds of motions that occur along this line. Okay, let's say that I wanted to plot, and here we'll call the distance from the origin as being my x displacement vector. Okay, so that's a vector, we notice here, because it has a length and it has a direction. It's in the positive x direction, and so x here would equal 2. So let's say that I stand here. What kind of a plot, think about this for a second, would you have for x versus t? This is 1, 2, and then here this would be -1, -2. Okay, it's probably the simplest kind of motion that we can illustrate with a graph like this. I think that a lot of you will agree that this must be a horizontal straight line. Okay, so this is indicating that there's no motion. If I'm just standing here at x equals 2, there's no motion. And notice that the slope of this curve is 0, and then it stays at 2. Now, does it stay at 2 forever? Well, no, because eventually I'm going to have to move. I have to get something to eat, I have to sleep in the evening, and there might be another person coming in, say at 12:30 or so, and go, well, Dr. Eichmeyer, would you mind moving so that we can use the board? And I go, well, no, I have to stay right here forever, because that's the plot. And then they bring in the guys with the straight jackets and they carry me away, and then tomorrow you have another instructor. So the domain of this function, this is x versus t. Okay, so this is time. It doesn't go forever, it just goes for as long as you're there. Okay, and so that's a little different sometimes from what you get in a math class, where the domain of the function extends to infinity, and you know that realistically that's not going to happen here. This just goes maybe for 8 or 10 seconds, depending on how long I can stay fixed in one position without fidgeting around. Okay, now, what if my plot looked like this, though? X versus t. Okay, so the time is on the horizontal axis. The x displacement, which is the vector, sometimes in your book this might be called x minus x naught, but we're calling x naught here 0, so that we don't have to worry about that kind of thing. But what if we had something where at time equals 1 second, this was my plot? Think about that for a second. Is that possible? Turns out that that would be probably not so possible, because this would indicate that I was everywhere at the same time. Okay, so at 1 second, I would be everywhere along this line. I'd be at plus infinity, I'd be at minus infinity, and I'd be everywhere else along that line all at once. So I'd have to have some kind of amazing powers to be able to pull that one off. And so this corresponds then to a slope of infinity. Okay? And so that would be the only way you could be everywhere at once, is if you were moving infinitely fast. But Einstein tells us that the fastest that anything can move is the speed of light. That's our speed limit. Okay? And so this is not possible. This is just standing at x equals 2 for a certain length of time and not moving. So we can then somehow get a feeling for the fact that the slope of this curve seems to be related to how fast we're moving. And in fact, that is the case. So what if I were to start moving along? Let's say that I start at x equals minus 1 at time equals 0. So that's down here. So I'm there at time equals 0. So we could call this minus 1 comma 0. 0 we'll do xy. So here this would be time equals 0, y equals minus 1. We'll use that convention. And then let's say that at time equals 1 second, we're at x equals plus 1. So now I'm here. After 1 second, I've gone from here to here. Okay, so then this point here would be 1 comma plus 1, indicating the time, which is the x-coordinate, would be first, and then the vertical coordinate would be second. And then if I go to x equals 2, then let's say that I'm up here at 3. This would be time equals 2, x equals 3, etc. Then we could draw a straight line through those, and then let me try to smoothly illustrate this kind of motion. Here's 1 second, 2 seconds, then 3 seconds. I'd be, I think you can follow the pattern now, I'd be at x equals 5. Okay, so this would be 3. So I go up here, this would be 3, and this would be 4, 5. This would be 3 comma 5. Okay, so here's a straight line plot. I can get the slope of that straight line plot. But I think that you can see that I'm covering 2 meters in every second. So you kind of already know the answer from the way that I have set up the problem and from the way that I'm plotting it here. My velocity should be 2 meters per second to the right. And so how can we verify that? Well, here we could call this T1 x1. We could call this T2 x2. And then we could calculate the slope. Slope then, and this is in general the average slope between 2 points, but if the slope doesn't change, the average slope is equal to the instantaneous slope because it's always the same. And if it's a straight line, we know that the average slope is in fact the same as the slope at any point on the curve. This would be x2 minus x1 divided by t2 minus t1. Or that slope is just rise over run. Call that the velocity. And another way of writing that then is the change in x divided by the change in the time. And so here, that would be equal to, well, x2 is 5 meters minus x1 minus 1 meter divided by t2, which is 3 seconds, minus t1, which is 0 seconds. So that gives us a change of 6 divided by a change of 3. Or that's 2 meters per second, which is exactly what our intuition told us was happening, because I was covering 2 meters in every second. Okay? And so I was just making a graphical representation of this, and so this is a constant slope and associated with that a constant positive velocity. And now what if I turned around and I went this way, but with the same speed? Okay, so remember that a vector has a magnitude and a direction. So if I turn around, the magnitude is, but I keep the magnitude the same, then all I've changed is the direction. So if I start moving this way, let's say I go from 3 to 1, and then from 1 to minus 1, and then from minus 1 to minus 3, that should just simply be a negative velocity that has the same magnitude of the slope, but a negative slope. And so let's see if that's how that works. So in other words, the velocity isn't decreasing because I'm going this way. It's just motion in what we're defining to be the negative direction. Now we could just as easily have defined this direction to be positive and this direction to be negative. But convention tends to favor choosing to the right as positive unless there's a compelling reason to change that. And we'll see that there are good reasons for changing to a direction that's positive that might point in what we would normally call the negative direction. But for the moment, we're not going to do that. Okay, so if I go from, say, 3 to 1 in 1 second, then I'm going to start out here with x at 3. This is 2, 1, 0, minus 1, minus 2, minus 3. Okay, so we'll start here then at 0, 3 for our initial time and our initial position. Then after time equals 1 second, we're at 1, 1. Okay, then after 2 seconds, we're at 2, minus 1. Then after 3 seconds, we're at 3, minus 3. So then if I've drawn these carefully, I see that, yes indeed, I've got a negative slope. If I call this here my t2, x2 value, I call this my t1, x1 value. And of course, I could do this any way that I want in terms of choosing any 2 points. I don't have to choose the extreme points in my data set for this, but that's just what I'm choosing to do here. Then our slope, which is the velocity for this curve, is going to be x2 minus x1 divided by t2 minus t1, which here would be minus 3. And then here we have minus 3, that would be meters, divided by 3 minus 0. And so that would give us minus 6 divided by 3 is minus 2 meters per second. So we don't want to think in terms of a negative velocity, meaning that we're slowing down. The velocity is still constant because the slope is constant. All that's happened here is that we've decided to go in the direction that was defined in the beginning of the problem as being a positive direction. And so now we're going in the negative direction.